Hey everyone, Alessandro D'Amica here. Welcome back to the workshop. Today, we're diving into something that's absolutely critical for any foundry or finishing operation, the quality of your steel shot. Using poor quality steel shot, it chews up your machinery, spikes your operating costs, and gives you a finish that's, frankly, subpar. Identifying this bad abrasive before it ever enters your system is one of the most important things you can do to keep your operations running smoothly and efficiently. The truth is, many of the most significant defects, like those pesky internal voids, are hidden from plain sight. But here's the good news. You don't need to be a metallurgist with a full-blown laboratory to get a really good idea of what you're working with. There are a handful of practical, hands-on tests and observations you can perform right here on the shop floor. In this video, I'm going to walk you through my 5-step process for spotting bad steel shot. My goal is to empower you with the knowledge to become the first line of defense against poor steel shot. It's about being smarter, not just working harder. So grab a sample of your shot and let's get started. Alright, the very first thing I do with any new batch of media is a thorough visual inspection. I start by spreading a sample thinly on a clean, well-lit white surface. This contrast is key. What I'm looking for first is uniformity in shape. Good quality steel shot should be, for the most part, spherical. I'm on the lookout for a high percentage of irregular shapes, things like teardrops, elongated pieces, or conjoined snowman-like pellets. These oddballs don't fly true in the blast stream and lead to inconsistent coverage and premature breakdown. Next, I get in a little closer and examine the surfaces of the individual pellets. I'm hunting for telltale signs of poor manufacturing surface cracks, which are weak points just waiting to fracture upon impact, and excessive pitting or roughness. A good piece of shot should have a relatively smooth, almost satin-like surface. If the batch looks overly porous or rough, it's a red flag. I also check for color uniformity. While there can be slight variations, a batch with wildly different colors, some dark gray, some almost silvery, some with rusty patches, can indicate inconsistent heat treatment or poor raw material, both of which compromise durability. Finally, and this one is huge, I look for the presence of excess dust and fines. When I run my hand through the sample or pour it from one container to another, I'm watching the air. Do I see a big plume of dark dust? Are there tiny sand-like particles mixed in with the full-sized shot? This dust does absolutely nothing for your surface preparation. It just clogs up your dust collector, reduces visibility in the cabinet, and adds to your disposal costs. Once I've given the shot a good visual shakedown, it's time to move on to a test that gives us a clue about what's going on inside. The density check. This is my favorite way to hunt for those invisible internal voids. Voids are essentially tiny air pockets trapped inside the shot during manufacturing. They are bad news because they drastically reduce the mass and kinetic energy of the pellet, and they create internal weak points, causing the shot to shatter prematurely. The easiest way to test for this is by measuring the apparent density. You don't need a fancy lab setup. A simple graduated cylinder and a good quality scale will do the trick. Here's the process. Take 60-gram steel shot, pour in 20 cc of alcohol in measuring tube. Then see how many cc the volume is increasing. Basically use Archimedes concept to get volume of 60 gram of steel shot. When you got volume and weight of steel shot, so can get density. A lower density directly translates to less impact energy on your part, meaning you have to blast longer, use more media, and put more wear on your machine to get the same result. It's a simple test of mass versus volume, and it's incredibly revealing. Now, for a quick and dirty trick that I love, there's the magnetic test. This one isn't about voids, but it's great for spotting non-ferrous contaminants or shot that hasn't been properly heat treated and isn't fully martensitic. All I do is run a strong magnet through a sample of the shot. Good, hardened steel shot should be strongly magnetic. Every single pellet should leap onto that magnet. If I find a bunch of pellets that are left behind, or if the magnetic attraction feels weak across the board, it tells me there are inconsistencies in the material composition or the hardening process, which again points to a product that will not perform or last as it should. Now we get to my favorite part, destructive testing. This is how we find out how the shot will actually behave when it smacks into a workpiece at high velocity. In a laboratory setting, this is done with a specialized machine that repeatedly fires shot against a hardened anvil, and the breakdown rate is carefully measured. But You know, we can replicate the core principle of this test right here in the shop with nothing more than a hammer, a solid steel block, and some safety glasses. Please, do not forget your safety glasses for this one. Here's my simple setup. I place a small representative sample of the steel shot, maybe 15 or 20 pellets, on a heavy flat steel anvil or a thick piece of plate. Then, I give it a single solid strike with a hammer. I'm not trying to completely obliterate it, just to subject it to a sharp, high-energy impact, similar to what it experiences in a blast wheel. The goal is to simulate a single working cycle. After the strike, I carefully examine the aftermath. What I'm looking for is the difference between plastic deformation and brittle fracture. What does good shot look like after this test? It deforms. It flattens out into a little pancake or a disc. This shows that the material is tough and ductile enough to withstand the impact, transferring its energy to the workpiece before breaking down. This is the behavior you want. It means the shot will last for many cycles. Poor quality shot, on the other hand, shatters. It explodes into multiple sharp, angular fragments. This is brittle failure, often caused by improper heat treatment or those internal voids we talked about. This kind of shot will break down almost immediately in your machine, creating massive amounts of dust and doing very little effective work. While our eyes are great for a first pass, sometimes we need a little help to see the finer details that separate good shot from bad. This is where simple magnification comes into play, or a basic digital microscope that you can get online for a very reasonable price will work wonders. Getting a magnified view allows us to confirm the suspicions we might have had during the initial visual inspection. It turns educated guesses into solid observations. With a sample spread out under the lens, I'm looking for the same things as before, but in much greater detail. Those hairline surface cracks that were difficult to see with the naked eye become glaring canyons under 30 times magnification. The subtle pitting and porosity on the surface become much more obvious, revealing a poor casting process. I can also get a much better sense of the overall shape consistency. Are the spheres truly round, or are they slightly ovoid or lumpy? Magnification takes the ambiguity out of the visual check and provides clear evidence of the shot's surface integrity. Now, if you really want to confirm the presence of internal voids, and you have the resources, you can go a step further with metallographic analysis. This involves mounting a few pellets in a resin puck, grinding them down to reveal a cross-section, and then polishing and etching that surface. When you put this under a microscope, it's the ultimate truth-teller. You can physically see the internal structure. Good shot will be a solid, dense circle. Poor shot will reveal those dark, empty voids inside. While this is more of a laboratory process, it's worth knowing about, and some suppliers might even provide this kind of analysis upon request. The final, and perhaps most crucial way to spot poor steel shot is to pay close attention to your equipment's performance over time. Your blast machine is the ultimate quality control inspector, and it will give you constant feedback. You just have to learn how to interpret what it's telling you. One of the most immediate signs of trouble is a sudden increase in the amount of dust your system is generating. If your dust collector bags are filling up faster than usual, it's a direct indication that your media is breaking down too quickly. That dust, remember, is just shattered, useless shot. Another key metric to monitor is your media consumption rate. You should have a baseline for how much new shot you need to add to the system per hour of operation to maintain a consistent operating mix. If you find yourself having to add new media more and more frequently, it's not because the machine is suddenly hungrier. It's because the shot you're using lacks durability. It's fracturing and being removed by the separator and dust collector at an accelerated rate. This is a direct hit to your bottom line, as you're literally throwing money in the form of abrasive out the exhaust. Finally, keep an eye on the machine itself and the parts you're producing. Poor quality, rapidly fracturing shot becomes sharp and highly aggressive, which accelerates the wear and tear on everything it touches. Look for abnormally fast wear on critical components like the blast wheel, blades, control cage, and cabinet liners. These parts are expensive, and replacing them prematurely is a huge cost. Also, examine your finished products. Are you struggling to achieve a consistent surface finish? Are you seeing changes in the raw value or the surface profile? Inconsistent media will produce an inconsistent finish and period. Your machine's performance is the ultimate report card for your steel shot. So there you have it. 5 different methods, from a simple visual check to monitoring your machine's health, that give you a powerful toolkit for assessing your steel shot quality. Remember that you are the customer and you have the right to demand a quality product. Don't ever hesitate to ask your supplier for a certificate of analysis for the batch you're purchasing. This document provides detailed technical data about the shot's chemical composition, hardness, density, and size distribution. It's a formal assurance from the manufacturer that the product meets specific standards. Comparing this certificate to your own hands-on test results is a fantastic way to verify that you're getting exactly what you paid for. No single test tells the whole story. The real power comes from combining these approaches. A quick visual inspection might raise a red flag, which is then confirmed by a low result in the density check, and proven definitively by a brittle failure in the hammer test. When you also notice your dust collector working overtime, you have a rock-solid case that your media is the root of the problem. This comprehensive understanding moves you from guessing to knowing, giving you the power to reject subpar materials before they ever cost you time and money. Ultimately, being diligent about the quality of your steel shot is an investment. It's an investment in lower media consumption, longer component life for your machinery, reduced maintenance downtime, and most importantly, a consistent, high-quality finish. You take control of a critical variable in your process, ensuring your operations are as efficient, cost-effective, and reliable as they can possibly be. Thanks for joining me in the shop today. Stay curious, and I'll see you on the next one.